Let's continue our discussion on designing a standalone PV system. In the previous video, you learned about modeling the battery bank by deriving an expression to calculate its operating voltage. In this video, you are going to learn how to choose and size different components in the standalone PV system, such as the battery bank, the inverter, and the PV array. This is a typical topology of a standalone PV system. It consists of the PV modules, the battery bank, the charge controller, the inverter, and the loads. The energy flow through such a system is as follows. Assume, for example, that the battery bank has a full state of charge and at a certain moment the load begins to consume power. Now the battery will supply energy to the load while its state of charge starts to reduce. Later, when the sun is available, the PV module begins to deliver electricity. This energy is sent to the batteries for recharging them. Now the battery is supplying energy to the loads and receiving energy from the PV modules at the same time. The whole idea of this animation is to make you understand that the energy in the standalone PV system happens via the batteries at all times. To design such a standalone PV system, it is important to decouple the PV module and the loads from each other and instead connect them separately to the battery through the charge controller. By following such a design approach, we can split the system into load battery bank combination and the PV battery bank combination, thus making it easier to analyze and size the different components in the system. First, let us begin with the load battery bank combination. As with any PV system design, you have to first get the information about the loads used in the system. This is obtained in the form of load profile, which provides the instantaneous power consumed by the loads and subsequently their annual total energy demand. Further, to calculate the size of the battery bank in the standalone PV system, the average daily demand of the loads is determined. It is obtained by dividing the annual energy demand of the loads by 365 days and is expressed in watt-hours per day. Once the information on the daily load demand is calculated, a particular battery is chosen for the PV system from the market. Its rated energy capacity, CN0, is noted by multiplying its open circuit voltage and its rated capacity. After this, an adequate number of autonomous days, CS, is chosen. As you saw in the video about the loss of load probability, this selection can be made using the following table as a guideline. For example, places close to the equator can have less number of autonomous days, while such number increases for higher latitudes. Next, the required total energy of the battery bank, CN, is determined. It is calculated by dividing the product of daily energy demand of the loads, chosen autonomous days, and a sizing factor SF with a maximum depth of discharge, DOD max. Here, DOD max is the maximally allowed depth of discharge of the batteries in order to prolong their battery life. It is normally chosen between 20 to 30%. Finally, from CN, the total number of required batteries is calculated by dividing the total energy of the battery bank, CN, with the rated energy capacity, CN0, of a single battery. Now the topology of the battery bank can be determined, that is, the number of batteries in series and in parallel. For the number of batteries in series, the nominal system voltage, V-nom, is chosen. Values for typical standalone systems are 12, 24, 48, or 96 volts. Then, the number of batteries in series is calculated by dividing the nominal system voltage by the open circuit voltage of a single battery. From this, the number of batteries connected in parallel is determined by dividing the total number of required batteries by number of batteries in series. The resulting value is rounded up to the nearest integer. Once the battery bank size is decided, the selection of the inverter is carried out. Unlike the grid-connected PV system, the inverter is selected based on the maximum power consumed by the loads at any instant in time during the year, or as a worst-case scenario, by adding up the power rating of all the appliances. This maximum power is denoted by PL max. The criteria for selecting the inverter are as follows. First, the maximum load power, PL max, should be within the operational range of the inverter. Second, the nominal power of the inverter, PDC0, should be approximately equal to the maximal load power, PL max. Third, the nominal inverter input voltage should be approximately equal to the nominal voltage Vnom of the battery bank. By following a similar procedure used in the grid-connected PV system design, a suitable inverter is selected based on the above-mentioned criteria. The inverter can be chosen from the Sendia National Laboratory database or directly from the market. In the grid-connected system design, after we had selected an inverter, we used an inverter model, such as the SNL model, to determine the AC power delivered by the PV system. You know that in such a model, the AC output power from the inverter is a function of its DC input power. In our current design step, at this moment, we know the AC power delivered by the PV inverter, which corresponds to the load power PL, but we do not know yet the inverter's DC input power. For the standalone system design, we are going to use the same SNL model on the selected inverter, but with a slight modification. Here, we are going to apply the SNL model to calculate the unknown DC input power of the inverter from the known AC output power of the inverter. This is achieved by inverting the SNL model and modeling the DC input power as a function of the inverter's AC output power. In this way, the power delivered to the inverter is calculated and subsequently its efficiency. After sizing a battery bank and the inverter, it is the turn of the PV array. For that, we are going to focus on the PV battery bank combination side of the PV system. In order to size the PV array, the energy balance approach is followed, similarly to the design of the grid-connected PV system. Here, the energy consumed by the loads and the PV generation are balanced over an entire year. Additionally, a sizing factor is also included. Note that the procedure to calculate the DC energy yield from the PV is explained in detail in the video Calculating the DC Yield. From this energy balance, the number of PV modules required can be calculated. It is equal to the product of the load demand and the sizing factor divided by the energy generated by a single PV module. Once the total number of PV modules required are determined, the number of modules in series and in parallel are calculated. The number of series-connected modules is calculated by dividing the nominal DC voltage of the inverter by the averaged maximum power point voltage of the PV module, as explained in the Calculating DC Yield video. Further, you have to keep in mind that this averaged maximum power point voltage of the PV module should be smaller than the maximum voltage of the charge controller to avoid damage to the latter. Also, the resulting value is rounded down to its nearest integer. To understand this rounding approach, you can refer to the video Calculating AC Yield. Finally, the number of PV modules in parallel is determined by dividing the total number of PV modules and the number of PV modules in series. Here, the resulting value should be rounded up to the nearest integer. To conclude, in this video we saw the sizing of the different components in a standalone PV system. The design of such a system is based on the concept that the flow of energy in the system happens via the batteries at all times, thereby decoupling the PV array and the loads. As you saw, the size of the battery bank is done with respect to the load. Then the inverter is determined, and finally the PV array size is calculated. In the next video, we are going to use the information we calculated so far and from the previous video to determine the performance of the standalone PV system.